Excuse me. All right, so again, welcome. Appreciate you joining us. Today's webinar on for our Six Sigma study series is design of experiments. Now, design of experiments is generally a structured approach to experimentation that we're going to see is going to be useful in many applications. And just to let you folks know, as we go through this, this is generally a presentation that we give to a live audience as well. I mean, in person, where there's actually a workshop with some activities. And what we'll do is y'all just kind of talk through some of those points just so you can get an understanding of what we would normally do and how it applies. The topics that we're going to cover today is first the experimental approach. Then we're going to introduce the topic of design of experiments. We'll talk about experimental assumptions that are made. Then we'll introduce comparative studies and screening designs as two types of methods that we would use in design of experiments. So we always start off, this is always a fun one, whenever we have food, you know, it always captures the attention. So apologize if I don't have any M&Ms in front of you right now. But you know, what we put out there is you know, a question that everybody wants to know, which is the most common M&M color. And then we go through and we say how we do an experiment in the class where we distribute bags of M&Ms and we go ahead and count them out. But before we do, we first kind of get a general sense from the attendees as far as their hypothesis. What do they think the most common color would be? And we make note of that, and then we go ahead and conduct the experiment. We look to see what we might expect. So we'll do a quick internet search, and believe it or not, there is a targeted mix out there for a given distribution of colors within a bag of M&Ms, and this is the distribution. So most commonly, you would expect to find blue at 24%. Next would be orange at 20%. Green then would be 16%. 14% for yellow, and then 13% for red and brown. Not very interesting to this point, but when we walk you through what we would normally do with our participants, you'll kind of see why that's going to be important. So one is we would state the hypothesis, and me personally, I made a prediction that blue would be the most common based on that information. Keep in mind that people still have their preferences on the vote that we did earlier on. So it's kind of builds up a little excitement within the room when we kind of see who comes out to be the winner. When we actually perform the experiment, at this point we ask participants to open up their bags and empty them out on the table, sort them out, count the colors, but we remind them, please don't eat them yet, because for those of you who do have some experience with experimentation, we don't want to introduce what's called bias in our study, or in some way influencing the outcome that would not be fair. So we go ahead and we analyze the results, and we ask folks which color they have the most of. Now, sure enough, when we have a room full of people, different folks have different colors. So some folks will indeed have blue as their greatest color. Some will have green, and even some of the lesser frequent colors, you'll have folks that maybe red is the most prominent color. So it's interesting to see how we have that distribution within the class, and it becomes very apparent that not everybody will have the same distribution of M&Ms when they've counted them out. And then I posed the question, well, what would happen if we were to combine them all? If we were to combine all the results from everybody's individual little bag of M&Ms, what do we think would happen? And more times than not, folks will come to the conclusion of, we'll have a better answer, right? Is generally the way they'll word it. And I agree. And usually, and I'll introduce some of the terms that we talk about in DOE, design of experiments. We'll have a more precise estimate of, the true population distribution of M&Ms, right? So the more information you have, the more confidence we would have of being closer to the truth. So Again, at this point, right, everybody has chocolate in front of them, and they're itching to eat their M&Ms, and you know, they voted on who, you know, which color they think would be more prominent. I kind of threw down the challenge of blue. And I'll be honest with you, not every time does it work out to be blue. Most of the time it does. However, you know, because of what we call sampling variation, it's very possible that on a given evening or afternoon when we're performing this experiment, the bags that we selected may not have blue as the most prominent color. So, you know, generally we tell them the winner is you, because after waiting, they can all now eat their M&Ms. But as I mentioned before, you know, it's always interesting. A lot of the learning comes through when we're actually conducting this live, because we don't know what to expect. You know, we have, you know, a high level of confidence that blue will most likely be the most prominent color, but not all the time, right? And that's a very real occurrence that you can expect in design of experiments, right? When we take a sampling, when we run an experiment, you know, we may get the result that we expect, but you know, due to sampling variation, we may not. And we're going to see how we can protect against that phenomenon. But just like I do in the workshop that we have, I kind of told the small white lie here as well to you folks. And when I introduced the M&M activity, I said that we're going to do an experiment. We're going to see what the most prominent color M&M is. And in truth, that is not what we consider an experiment, right? And at this point, you're probably asking, Anthony, this is a webinar now on design of experiments. Why did you run me through this just to tell me that we did not do an experiment? The reason why is very often folks will confuse, whether it's design of experiment, scientific method, what have you, they'll confuse that activity with what we actually call an observational study. And an observational study is something that happens when we're just observing what already exists and we're not trying to influence the outcome. Okay, and in this example with the M&Ms, yes, one can argue that we're trying to influence the outcome with, you know, the number of bags of M&Ms and such, but that really doesn't necessarily change the true outcome, right? We're not influencing the M&M factory and how they're producing the color of M&Ms and bagging them and such. We're just observing what already happened. Whereas in an experiment, you're going to see that not only are we going to be observing a particular outcome, we are also going to be changing the inputs in an effort to influence the output, okay? And by doing that, we would understand the relationship between the inputs and outputs, and that'll give us a great advantage. So let's talk about this experimental approach though. So if we decide that we want to do an experiment, next question is, well, how do we get started? Where do we begin? And you know, the most natural place for folks to want to begin is what's called the best guess approach. This is where folks would select an arbitrary factor or setting combinations, test and adjust based on the response. So the proverbial, what I call tweaking the knobs, where you set if it's a machine, you set a machine up, you turn a knob. Maybe it's a different type of, maybe a business process where, you know, you change the questions that you're answering or the sequence of activities that you do. Whatever it is, there's a best guess out there, and you go ahead and you try changing all these things and you see what you get. Not very scientific. The next would be what we call one factor at a time, or OFAT. And this is where we select a baseline for all factors, but then only change one at a time, right? So if I had 5 different things, that maybe vary. So whether it's 5 knobs on a machine or 5 other factors in my business process, 5 sets of questions that I can ask, or 5 different sequences, whatever that is, and we only change one at a time. Again, intuitively, it may make sense, but there's significant shortcomings with that approach. And both of these approaches are neither efficient nor effective in determining what we call potential interactions, right? Where the outcome of the final result based on one setting could be influenced by another setting. And the example we always use here, say, when you're cooking, time and temperature are two factors that are related, right? So as I increase temperature, I have to decrease time, right? And vice versa. Now there's a right combination of those two that will give you the perfect result or the optimal result. But either way, if I increase temperature and I leave time set, I stand a chance of burning whatever I have or overcooking. So that's an example of interactions and why we want to understand the relationship. So design of experiments, if we can't use those two techniques, which are very intuitive and folks would naturally want to lean towards, what can we use? And the concept of design of experiments, or the field of design of experiments, was put together as a structured approach to experimentation. It allows us to accept several input variables, or what we call factors. It allows us to identify what we call the significant factors from many. So if there's multiple things that I believe could have an influence on my output, but I don't know for sure, we can use design of experiments to determine which ones really are important and focus on those, and maybe disregard the others that really don't have much input or influence on the output. We can use it to establish a model for the response variable, right? And that's that mathematical equation, the relationship between inputs and outputs, which again gives you a significant advantage because you'll have an understanding of predictability. If I do this, then this will happen, that cause and effect relationship. And then once you understand that, you can take one step further and determine that optimal level for each factor. As I mentioned before in the cooking example, there's a right combination of time and temperature that would work well for whatever you're cooking. If you're baking a cake, it's probably a little bit more tighter and constrained, and you really can't change it much. If you're cooking, say, a piece of meat, depends on how you're preparing it. If it's a roast and you're roasting it, it could be higher temperature, shorter time. If you're trying to smoke it at a low temperature, you want different result. Same cut of meat, it'd be much lower temperature, longer time. But again, it's understanding the response variable, that output that you want, and then experimenting to understand what those the settings for those factors should be, the inputs, so you can get the output that you want. The experimental assumptions that we have then must be kind of verified to make sure that whatever we come up with is valid. So we can run an experiment, we could get a result, but if we fail to verify these assumptions, then it's very possible that those results are invalid. The first is what we call measurement system capability. If I have a response, I'm measuring it somehow. There's some way that I'm measuring it to quantify how good it is if it's close to my target. Measurement system capability is the assessment of the measurement method to ensure that basically we trust the data, we trust the information, the measurement that we're taking. The second is process stability. If your process isn't stable and it's not necessarily predictable, meaning if for a certain configuration of settings or inputs, factors that we get a particular output. If the process is not stable, if the method is not stable, then if I run those same settings again, I might get a totally different answer. And that stability will basically give me erroneous information. So we want to make sure that process stability is there. And then the last one is one that's often overlooked, and it's called the behavior residuals. So what residuals are, it's a little beyond the scope of this, but just to give you an idea, I mentioned earlier that we're going to get this mathematical model. Now, I should also say that those of you who, maybe math's not your favorite subject, that's okay. There's software out here that does this for us. But in any event, we like to have that mathematical model because, as I mentioned before, it allows us to make some predictions. It allows us, if I want a particular output, it allows me to predict what inputs can give me that output, or vice versa. If I want to run at certain settings, it can tell me what that output might be that I can expect. Well, nothing's ever perfect, and a model is just a model, and it's not exactly what you would expect every single time. There's a little, what we call experimental error in there, where there will always be some level of variation. The residuals is, if I were to run this study over and over and over again, and I get actual data and I compare it to the mathematical model, if I subtract one from another, what's left over is the residual. And those residuals need to behave a certain way. Not sure if we have this in the presentation. If we do, we'll see it twice. One is that the average of the residuals is 0, meaning I could be just as much over the mathematical model as I could be under. They should be called what we say is normally distributed, or the traditional bell-shaped curve that we've learned in school, where it's symmetrical from one side and the other, and it has this nice gradual shape. The MSA and capability studies would answer the first two, and then the residual analysis answers the third. This is basically the part that I mentioned, how we calculate the residuals. And as I mentioned before, residuals actually allows us to estimate the experimental error. You always hear about experimental error, and you know, folks who, you know, maybe not familiar with these methods will just say, well, you know, they just kind of chalk it up to experimental error, and it's kind of more of a, lack of a better word, an excuse, right? So if it doesn't quite work out, they'll just say, well, you know, there's that part of experimental error that, you know, we have to account for. Residual analysis allows us to make an estimate of that. And as I mentioned before, we say normally distributed independently, meaning that they don't depend on one factor or another. And then distributed about 0, meaning the average is 0. With constant variance, that's the part we didn't mention before, meaning that my overall spread or variation of residuals should not change over the model. DOE guidelines, these are you know, just kind of some steps that you would want to go through when setting up your design of experiment. First and foremost, and this is any problem or anything that you're trying to resolve or make better, state the problem, right? Clear state of the problem. Select the response variable. Understand what it is that you want in the outcome, right? Stephen Covey will even say, begin with the end in mind, right? You want to know where you're ultimately trying to get to. Then from there, decide what the factors you're going to use, the levels and the experimental ranges, right? What adjustments you're going to do. And then choose the experimental design. And we're going to introduce a couple designs here, and there's many more. And then you actually run the experiment, right? So this is where, as I mentioned before, if it's an experiment, we're changing inputs, we're measuring the output, we're collecting the information. We'll do the analysis, and you know, for those of you, like I said before, you might not like math. If you don't like math, you're not going to like statistics either. But that's okay, because again, there's software out there that does this for us. You know, we perform the statistical analysis of the data, and then from that, we based on you know, some bias that we're introducing, right? So I select all the good ones first, and I run those, and or all the easy ones first, right? I don't want to do that because it could influence the output, which is a type of experimental error that we want to try to avoid, which is why we do randomization. Blocking is another one, where we create these blocks of relatively homogeneous groups, and that helps us remove the within group variation, so that I can easily see, you know, between group A, group B, and group C, I can see the difference, but the ones within each group should be close to one another. And then what we call replication. These are independent repeats of each factor combination. This allows us to estimate the experimental error. As I mentioned before with the residual analysis, if I run the same settings over and over and over again, I should be able to see a difference between my actual data and the mathematical model. that allows me to estimate the experimental error. When you are choosing factors, here's some things you want to consider. You want to understand what potential nuisance factors are. And what nuisance factors are, those are not necessarily the factors that you're interested in. Those are, either they're controllable more, a lot of times they're not controllable, which is what makes them a nuisance. And, the design strategies that we have can help kind of offset any influence that these nuisance variables or factors can have in your study. The first one is, if you don't know the nuisance factor, obviously it's not controllable. You can't not know it and then try to control it because you don't know what it is. So if it's unknown, you obviously can't control it. That's why we do randomization, right? Randomization kind of takes into account, we don't know what's out there. So if I randomly select it, I have just as much chance of, hitting that nuisance factor as I don't. And because of that randomization, it should neutralize that. The other type is, if it's known and controllable, well, if it's controllable, I could set it up in blocks. I can strategically control my factors into these blocks so that it groups things together and it can ease my analysis. And then the last one are ones that are known but uncontrollable. Temperature, right? Ambient temperature is a good example of that, right? You're really in a room, you can do that, but if it's something that you're doing outside, you really can't control the outside. We use what's analysis of covariance, and that's where I can't control the factor of temperature, but I could still measure it, and I could log it down with my data. And then when I do my analysis, I just say, well, there's a covariant factor in this column over here. Do that analysis and help me out. Remove that error term from my study, please. Again, software does that for you. And by knowing this, and again, you're going to see that planning the DOE is probably more important, probably the most important step than just analyzing the data. A lot of times folks come with me, they ran an experiment, they give me the data, but not knowing the plan behind it, I can't always give them the best answer. And a lot of times we find out it was a bad experiment. This experiment itself was not good, or the data is not valid. So appropriate design strategy allows us to remove that experimental error and have more confidence in the outcome. So what kind of designs? I promised that we'd talk a little bit about some designs. The number of factors and the experimental objective help us define or determine the appropriate design. If I only have one factor, if there's only one variable that I can change to change the output, what we do is we're only doing a comparative study at that point, right? I just want to compare one level against another, one setting against another, one variation of this factor against another. We're going to do a comparative study, and we want to completely randomize that, right? We don't want to introduce any bias into the study. Now, if I have 2 to 4 factors, if the goal of my study is to do a comparison, one, we could do a randomized block. But 2, if I have a different objective, if I want to screen out, if I want to know what the most significant factors are, or if I want to characterize, if I want to come up with that mathematical equation, I can either run what's called a full or fractional factorial. We'll talk a little bit more about those later. And if I'm trying to get to that next level of characterization, or I want to optimize it, I can use a more sophisticated design. One is a central composite, another is a box Penkin. Those are going to be beyond the scope of this webinar today, but just know that there's a natural progression, right? That you would go from screening to characterization to optimization. And sometimes the full factorial design can get you everything you need. If you just wanted that next level of optimization, you may want to use some of these more sophisticated tools. Now, if you have 5 or more factors, again, comparative study, you're still going to do a randomized block design. But if you're screening or characterizing, you're going to step off of the full factorial, and we're going to see why. Just to give you a hint, as you add the number of factors, the number of experiments you have to run grows exponentially. So when we start introducing 5 or more, you end up coming up with a lot of work. So, but we can still use the fractional factorial. Allows us to do. We still get a lot of great information with less runs, so it's very efficient. But there's also another design called Plackett-Berman, which also is very effective on screening. if our goal is to characterize or optimize, again, if we have 5 or more factors, more times than not, they are not all significant, and you're going to find that you could probably reduce it down to 2 or 3. So the strategy there is going to be screen first, right? Go back to your screening, make sure that you've really narrowed down the list to the most significant factors, then come back when you have 2 to 4, and you can look at maybe using the central composite or the box Benkin. So the purpose of comparative studies, as I mentioned before, comparing one thing to another, it's to determine if there's a statistically significant difference among the effects of various treatment levels. What that means is if I run this setting and I get an outcome, run the other setting, get an outcome, if I do that enough times, I want to see if not only is there a difference, but a statistically significant difference, right? Because sometimes you could see a difference, but it's just by chance alone. So we are looking to leverage some statistical analysis to confirm with a certain level of confidence that there's a real difference. And this course is, this webinar is part of a broader course that we teach. So there are some basic statistics, statistical analyses that we've introduced. So you can use a t-test, an ANOVA, etc. But at the bottom line, a properly designed experiment will consider also the nuisance factors in the design and the analysis of the results as well. So if we are running a comparative study, question is, what options do we have? So we mentioned before the randomized block design. Then we have the Latin square. It's called the Greco-Latin design, and then hyper Greco-Latin. We're going to just breeze through these at a high level. Again, there's lots of materials that kind of go into them in detail, and this presentation will be made available to those on the call today, so you can go back and revisit them as well. But just want to touch on each of these just to kind of show overall what the design entails, when you might use each one. So the randomized block design, it accounts for both unknown and uncontrollable as well as known and controllable nuisance factors. This actually, in design of experiments, this actually came out of the agriculture industry a long time ago, and it was because we wanted to optimize crop yields. Now, that goal is an admirable goal, and we could certainly apply that to anything in business that we do now. But because agriculturally it was kind of born and raised, a very natural example that we use to kind of visualize what a randomized block design would be a garden plot. So you have a garden plot, and we want to establish these blocks. Now, why would you do that? A nuisance factor could be the way the sun rises and falls, the way we have irrigation, what have you. So what we do is we'll actually, map out strategically a plot on the in the garden. So we have block number 1, block number 2, block number 3, block number 4, and then within that, we're going to randomize the want to be able to separate that out and truly understand what the difference is due to fertilizer alone, and not necessarily the irrigation, what have you, right? Because those are things that maybe I can't change, or definitely the sun, right? I can't change. The sun goes from east to west. I can't change that. So basically, that allows us to remove those factors and just narrow in on the factor of interest, in this case, the fertilizer. A Latin square design, it's going to look very similar. Now, let me just go back real quick. As I mentioned, the treatments, what we call the treatment inside each block, is completely randomized, meaning they could show up in any order. We see fertilizer A was the first one in both 1 and 3, okay? Just want to point that out, because in a Latin square, and the next few that we're going to look at, it's not quite randomized, all right? We didn't quite random. There's a little bit more sophistication in this design. And again, you don't have to know how to do it. There are books, lookup tables, things of that nature that give this to us. But the Latin square allows us to set up an experiment when we believe what we have, when we have two nuisance factors. In manufacturing, and we say nuisance, guys, don't take this the wrong way, right? Some of you are going to say, hey, operators, they're not a nuisance. That's not fair. When we say nuisance factor, it's, you know what, when we hire folks, right, there's going to be variation, okay? We're not going to change that. And at any time on my manufacturing line, I should run a process so that basically any operator should be, valid to use in running my manufacturing. Same thing with the batch, the batch of material that comes in. So, I know that there's going to be variation between people. I know there's going to be variation between batches, but what I really care about in my study is the actual method that I'm going to use, right? Maybe it's a gluing process or an assembly process, and we come up with 4 different variations. We call them A, B, C, and D. And we ask each operator, right, giving them different batches of material, we ask them to try these different techniques. Technique A, then try technique B, then try technique C and D, and so on. But the difference between this and the prior example is that the factors are no longer randomized. They're structured in a way to what we say provides balance in both rows and columns. And what I mean by that, if you look across any row, each treatment, each letter will be represented once and only once. And if you also look in any column, again, each treatment or each letter will be represented once and only once, okay? And that gives us balance so that we're not biasing the study one way or another, and it allows us to evenly remove the effects of the operator, the effects of the material, and only analyze the effects due to treatments A, B, C, and D. If the Latin square then allows us this structure to compensate for 2 nuisance factors, the Greco-Latin allows us 3, where the structure is still the same, where I have the operators along the top and then material along the side. The second nuisance factor is introduced as a second letter or second treatment within the matrix. Hence Greco-Latin, we add a Greek letter to alternate. So here we had A, now we have A and alpha. B, we have we have A and alpha in this one case, but we're going to find out that A could be paired up with others as well. So, going through this matrix, we find out again, it's going to be balanced in both rows and columns, meaning that if you look across, A will show up once and only once, B, C, and D, the same thing for the Greek letters. They'll show up once and only once in each row, once and only once in each column. The hyper Greco-Latin square then allows us for comparative study analysis, as I mentioned before, also use the analysis of residuals. If you look in the middle of the slide here, the software of choice that most of us will use is what's called Minitab, provided by a company called Minitab. There are others as well, but this is the one that's most commonly used in industries that are looking for quality and productivity gains. And this would be an example. So on the left-hand side, again, there's math behind this that does all the analysis for us. It comes down to interpreting the analysis of variance output as well as the graph on the right. Here we see that there's a significant difference among additives. This was a manufacturing process where they had different additives. We know, and I'll point out how I know, and if you want to learn more, we can bring that up in another topic. But we see that the significant difference among the additives by looking in the rightmost column, what's called the p-value. And if the p-value is very small, in this case it's 0, we can say that there's a statistical difference in this factor we call additives. And then if I look at on the right-hand side, if I look at that chart, again, that residual analysis, I'll look in the upper left-hand corner, and most of my blue dots fall on that red line. That's usually a good indication that they're normally distributed. And then in the lower right-hand corner, I look at that zigzag blue line that that goes about the dashed line. We see that the dashed line is representing the average is about 0, and the variation is pretty much constant over the whole range. So qualitatively, right, we've met the assumptions. The residuals look good, so I trust the model and say, you know what, there is a difference among additives. We know that at least one of those additive choices is going to be significant, and then we'd understand which one gives us the best response. So the design of experiments, that was just a comparative study, but real power design of experiments comes when we have more than one factor. We have multiple factors that we want to understand, which ones are important. We introduce the screening DOE. And we always use this funnel as an idea because I start off with a lot of information and I want to slowly whittle it down to get down to what's really only most important and where I really understand what's going on, and I could make predictions about my process and the output. So we do the screening to identify the vital few among the trivial many, and it allows us to use statistics to reduce those factors down to only the most important ones, only the ones that really make change on the output. Then we do the characterization. Okay? We want to determine what's called the process transfer function, this magic function y equals f of x. Right? I can tell you what the output is going to be based on the input. Right? As I mentioned, there's a lot of power, a lot of advantage of knowing that. And through that, we could also identify what we call the process limits and challenge conditions. There's some industries that they have to do what's called process validation, meaning repeatedly producing DOEs that we can kind of push the process. And then the optimization. This is where we could define robust process parameters and identify that the ideal process settings to maximize what we call capability, right? The most predictable, highest performing output that we can possibly get. So if we start at the top of that funnel, we want to introduce screening designs. And just like we did with the comparative study, when I say screening designs, that's a strategy. The tactic will be, which one do I choose? And we mentioned earlier, there are 3 that we basically choose from. There's full factorial designs, fractional factorial designs, and placar permanent. You're going to see some additional slides here. There's going to be quite a bit of math. Again, we're going to fly through those. You can review those again at your own time. But we'll basically walk through how the math works behind. Again, you don't need to know that because software does it for us. Software will do the analysis. But sometimes it is good to know kind of the inner workings of how the process goes, because often, experiments won't quite work out the way you wanted, and you need a way to diagnose and troubleshoot. By understanding how the analyses are performed helps kind of give you clues as far as what went wrong so that you could go back and fix it. So let's introduce factorial designs. Many experiments will require the study of the effects of 2 or more factors of interest. Factorial designs include factor combinations, meaning that since I have more than one thing to change, I can have different combinations of those things. We're going to see how we can analyze what's called main effects and interaction effects, and they're both defined as the average change in a response with the change in the factor level. So, I'm going to make all these changes. I want to see what the average change is based on certain settings, and it's that average that I'm going to determine if it was significant or not. A main effect, as we introduced earlier, that's an effect or an estimate of the effect of a factor that's independent of any other factors, right? So if all I did was change A from high to low, what is the net effect of that setting change on my output, independent of anything else. An interaction effect, kind of introduced this earlier with my cooking example. It's an estimate of the effect of a combination of factors, where the effect of one factor on the response is dependent on the level of at least one other factor. It's kind of the technical definition, but as I mentioned before, you could just visualize, if I increase temperature when I'm cooking something, chances are I have to decrease the time so as not to overcook. And vice versa, if I decrease my temperature, chances are I'll probably have to increase the temperature. And you know, but not every combination results in a good meal either. So you know, that's where this succession of experiments comes in. Factor plot example. This is an example of you know, what the software can put out for us. On the top right-hand corner, we have what's called a Pareto diagram. It's a bar chart where we put things in order from biggest to smallest. And the interpretation of this output would be, if I look at that red line, if the bar crosses the red line, if any of those you know, how that effect is, right? So in this particular example, and this looks more like a manufacturing example, if I increase time, I can increase yield, right? So if I go from a low, on the lower left-hand side, if I go from a low time to a high time, I could see that I stand to increase my yield. So that's favorable. So I'll probably choose a higher time. Similarly, if I go from a lower temperature to a higher temperature, then I can increase my yield as well. So chances are I'll probably want to be looking to increase both time and temperature. Then in the lower right-hand corner, that's called what's called a interaction plot. Now, we say that there's no interaction if these lines are perfectly parallel. If they intersect, we say that there's a strong interaction. Now, in this particular example, they don't intersect. But if you were to kind of, you could see where they eventually would on the low side, right? Eventually they'll intersect. And that's why in the Pareto diagram, that interaction AB, that's why it's showing that it does have an effect, right? The interaction is significant. It's not as big as the other two, right? A alone and B alone have a stronger effect. But it's still there, and we'd still want to consider it. When doing factorial designs, we want to include all possible level combinations for each factors for the full factor. A fractional factorial designs allow us to run the same experiment with only a portion of all possible combinations for each factor. Now, while I said before, it still gives you good information. Obviously, when you take something away, you do lose a little something, right? And the thing that we lose is what's called resolution. Resolution defines the level of confounding or aliasing, right? Not being able to tell the difference between certain things in a fractional factorial design. This is a listing of the resolutions. Again, this is something that you could go through. Generally, resolution 2 is a useless design. That means we can't even tell the difference between two main effects. We don't use those. At a minimum, we're looking for resolution 3. Now, what that tells me is that I might not be able to tell the difference between a main effect and a two-way interaction. But if I'm just doing a screening, that's perfectly fine. As I'm getting more sophisticated and if it looks like I have a more complex mathematical model, I may need to go higher resolutions. But you don't necessarily have to start off there. Again, Minitab is a great piece of software that will help you identify the resolution. It'll tell you if you choose these number of factors and you want to do these number of runs, it'll tell you what the resolution is. So you can go in knowing, knowing the possible limitations of your design. This is experimental notation of factorial designs. We have levels raised to the power of the number of factors. Mnemonically, we like to say levels lie, factors fly. And this tells you how many experiments you might need. For an example, if I have 5 factors at 2 different levels, and generally, we'll be running 2-level factorials. 2 to the 5 means 35 different experiments, okay? And that's why I said before, right, if you have 5 or more, you may want to consider something else because it quickly grows to be a significant number of experiments. So if now I choose to do a fractional factorial, I could do what's called a 2 to the 5 minus 2. So I still have 5 factors, but I'm basically cutting the number of runs by a factor of 4. The reason why it's factor of 4, it's 2 to the 2, which would be 4. I now only have to do 8 experiments, okay? It's probably going to be a resolution 3 experiment, so, you know, I lose a little bit of information, but if I'm just starting off, that's perfectly fine. I could get the answer that I need with only 8 runs instead of 32. So there's a lot of efficiency in running a fractional factorial. This is the example that I'm just going to flick through real quick. This is what an experiment might look like, and then when we run the experiment, we collect the data. I'm just going to run through these without going into great detail, but basically what we're doing is we're calculating the average effect based on different combinations. So this would be the effect of temperature alone. Then we look at pressure, and we calculate that average difference. We look at the average difference for concentration, okay? And then we expand it to do the interactions as well. And then we run the same analysis. Again, don't get too hung up with the math. Minitab will do this, but it is interesting to see that as we run through this, it's just basic algebra. We're just basically taking averages of differences depending upon the setting of a factor that I'm looking at. And this would be the difference for the 3-way effect. So interpreting the results. In the end, temperature and pressure appear to have a strong effect on the yield, for concentration not so much. We look at the main effects. We see that the effect of temperature has a positive effect, right? So if I increase temperature, I can increase yield by 23%. Pressure, on the other hand, has a negative, but that's okay. That just means I need to go down, right? So if I lower my pressure, I can stand to gain 6% in yield, right? But if I increase pressure, I would have lost the 6%. So we want to decrease so that we can flip the sign of that 6. Concentricity, it's only 2, right? There's still something there, but compared to everything else, if I only wanted to dial in, you know, two parameters, temperature is going to give me the best return on my investment. The 2-way effects, very small, right? Hardly any, you know, either a half or 0. And then the 3-way effect, again, is relatively small. So we can do what we call the reduced model, where we see that the yield is going to be the overall average, which was 64, plus half of the effects. Why half of the effects? Remember, the study we increased and decreased. We went above and below some average setting, and when we come up with the model, we're basically saying, okay, well, if we ran at the average condition, what could we stand if we go high? What could we stand if we go low? And it's basically half of that effect. So either way, though, I mean, if I'm running at my average settings and I increased my temperature, I ran at the high temperature setting, and I ran at the low pressure setting, and I ran at the high concentration, I can get close to 79.75% yield. Now, if we went back and looked at the experiment, we see that because it was a full factorial design, we had all combinations in there, and that aligned with experiment number 6. Remember that number, 79.75. It's just about 80%. Here's a fractional factorial example. And again, when you look through these notes, you know, when you're reviewing this webinar, just know that this is the same exact experiment. It's literally half of the data that we previously had. And I do want to note that run number 6 is not in here, right? You have run number 2, 3, 5, and 8. And again, software helps you pick which ones to use, but those are the ones that are in there. It's a resolution, as we call it, a resolution 3 design. Instead of running 8 runs, though, I only had to run 4 of this experiment. And if we run through the analyses in the same way, where we calculate and we compare side by side the results of the full factorial to the fractional factorial, we see that the main effects are very close, very close in the second experiment as they were in the first. 23.5% for temperature, -6.5 compared to -6, and 2.5 compared to 2. Interesting, though, the two-way effects, they look significantly different, right? They look very high. But if we look at those numbers, what we see is that those numbers are the same exact numbers that we had in the fractional, in the main effects, just kind of different order. That's what we mean by aliasing. That's what we mean by confounding. We can't tell the difference between two-way effects and main effects. So what I calculated for my main effects is going to be the same calculation for my two-way effects. Again, in this experiment, since we're only looking to screen and understand what the main effects should be, I could still go with, you know what, let's not look at the two-way effects. And then three-way effects, I can't even calculate that. Now, if we do the same approach, where if I took all those 4 runs and I came up with the overall average, and I took those half effects from the main effects, you know, the high temperature, the low pressure, and the high concentration, I come up with a value of 79.5. Now, remember before, when we did the full experiment, it was 79.75. Again, I said close to 80%, right? Now, what's a special interest, very interesting here, is that it's very, this is the prediction that we would have got if we were to run those conditions. That was in experiment number 6, or run number 6 in the original experiment. We didn't run that experiment. We didn't run that combination in this fractional factorial, yet we were still able to predict that that would be the best combination, okay? Just to show, right, and we use this as an example, just to show there's a lot of strength and efficiency in even fractional factorials. Plackert-Berman designs, again, we'll go through this very quickly. They're a type 3, they're a category of resolution 3 designs, and we'll typically use them for screening when we have a large number of factors. N is generally going to be a multiple 4 in this case. Again, we would see similar examples. This is one where, if we have 11 different factors, we can do that in 12 runs. And similarly, software does this, but mathematically, it's kind of the same way, where it calculates averages of different settings. This is a typical output from Minitab. And as I mentioned before, interpretation, if we look at that Pareto, we see that the bars that go over the red line, those are significant. Those that don't, aren't. So we could reduce those from the model, and we could, and at this point, and this is where the screening, the power of the screening comes in. We see that out of the 11 that we had, only 5 of them are significant. So the other 6, I can just forget about those for now, just set them to some nominal, or not consider them at all, and now I can just focus my energies on these 5. And then from there, I would probably run another experiment on those 5, just to make sure that out of all those, that they truly are significant. So wrapping up, we introduced the experimental approach, design of experiments, the importance of experimental assumptions, comparative studies, and screening designs as well. As I mentioned, we also introduced kind of a roadmap for design of experiments, where it's a succession of experiments, and you progressively get more and more information as you go on. That's all we have for today. As far as content, I'm going to open up now. If anybody has any questions, I'm going to take folks off of mute, or you can type in any questions on the message. Any questions? Hello?
Hello. Hi, Anthony. This is Himadri.
Audrey, how are you today?
Good, good.
Do you have any questions on the design of experiments?
Actually, I heard this lecture before from you, so this is the second.
Oh, perfect.
Yeah,
okay.
it was a revision for me.
Excellent, excellent. So anything kind of stand out in this time around compared to the first time?
Yeah, there are some more points you added to this lecture. I have heard. Yeah, I come across some of those things. I need to go through them once again because
Absolutely.
it was really tough to understand for me, but I have to go through them once again. So
Right.
just one question: how can I download this, presentation or the PPT? Can I get it
Sure.
from?
Yeah, that's a great question. So after the webinar, what we're going to be doing is we'll send everybody a link where you can get this training, as well as I mentioned before, this is kind of part of our Six Sigma study series.
Okay.
And we also have, actually, if I quit out of here, in addition to this, we also have a study guide or a preparation guide, and we'll make this available to everybody as well. It's 4 steps to Six Sigma certification, where kind of walks you through the value of Six Sigma training and certification. Give you some good links for some resources and preparation, including additional, if you want to learn more about design of experiments. We have a couple books here. There's some links to some books here as well that can help. But yeah, keep an eye out in your email for a link from us, and we will make these materials available to you.
Sure.
All right.
Yeah. All right.
Thank you, Madhuri.
Thank you, Anthony.
You're welcome. Any other questions? All right. Then if there are no more questions, again, I'm going to put everybody on mute. And I would like to take one last time to thank everybody for joining us today. Really appreciate you taking some time. Hope you learned something. And if you have any questions on this topic or any other topics that's in the Lean Six Sigma body of knowledge, we'd be more than happy to help you out. We run these series every month, so get on our mailing list, and we'll make sure that you're made aware of upcoming events, and hope to talk to you next time. Thanks again, and have a great day. Yes?
Just a moment. This is going to be a monthly series or a weekly series?
Monthly.
Oh, okay. Okay. All right. Thank you.
Yes.
Yeah.
You're very welcome. All right. And thanks again for joining, and everybody have a great day.
Yeah. You too.
Goodbye.